Kafka, RabbitMQ, and SQS look similar on the surface. They're not interchangeable. Picking the wrong one can cost you months. And before you even pick a tool, there are 4 concepts you have to get right, or your system will take itself down the first time a downstream service has a bad day. Pub/sub versus point-to-point, delivery guarantees, dead letter queues, and backpressure. Let's go. Before we even talk about queues, let's look at the problem they exist to fix. Checkout calls inventory directly. Inventory slows down, doesn't crash, just slows down. Checkout threads pile up waiting. 300, 400. Checkout is out of threads. Anything depending on checkout is now also down. One slow dependency, 3 broken services. This is called cascading failure. The real cause is overload feeding on itself, retries piling up, threads exhausted, queues filling, and synchronous coupling is the thing that lets it spread. Now watch what happens with a queue in between. Inventory slows, messages accumulate in the queue, checkout doesn't care. It writes and moves on. That's the whole point of a queue. It decouples the producer from the consumer in 3 dimensions. Time, they don't need to run at the same moment. Availability, one can be down without taking the other down. And speed, the fast one isn't held hostage by the slow one. A team shipped a feature on a Friday. By Monday morning, every new sign-up was getting 50 welcome emails. The root cause was one conceptual mistake. They'd put a work job onto a topic that fanned out to every consumer. 50 workers, 50 copies of the job, 50 emails per user. One question asked once in review would have saved that team their weekend. Should this message be handled once, or should multiple services react to it? Handled once means work. Resize this image, charge this card, send this one email. Any worker can grab it, but only one does. That's a point-to-point queue, also called a work queue. Reacted to by many means event. An order got placed. Inventory cares, email cares, analytics cares. 3 independent reactions to the same fact, each one its own copy. That's pub/sub. Sending a welcome email is work. One job, one send. The team put it on a topic, the topic did its job and fanned it out to every consumer. The tool wasn't broken, the semantics were wrong. And the vocabulary is also problematic. People will say, put it on the Kafka queue or the RabbitMQ topic and mean different things on different days. Don't argue about the word, ask what actually happens to a message when it arrives. Now, delivery guarantees. You'll see 3 delivery guarantees advertised. At most once, at least once, exactly once. And one of those 3 is, to put it mildly, misleading. At most once is fire and forget. Send it and don't check. Fine for metrics where one drop data point doesn't matter. At least once is what most systems use by default. The producer retries until it gets an acknowledgement. If the ACK gets lost, the message gets resent. You don't lose anything, but you can get duplicates. Exactly once is where vendors get creative with marketing. So let's just say it. Exactly once delivery across a network isn't achievable in general. Not in Kafka, not in RabbitMQ, not in anything. It's a property of distributed systems, not a vendor feature. It's closely related to a result called the 2 generals problem. Picture it. A producer sends a message, the broker gets it and sends back an acknowledgement. The acknowledgement vanishes somewhere on the wire. Now the producer has to pick, retry, and maybe cause a duplicate, or give up and maybe lose the message. The network doesn't tell it which situation it's in, ever. So when a system advertises exactly once semantics, what's actually under the hood is at least once delivery plus either idempotent processing or transactional rights. The message might physically arrive twice, but the effect of processing it happens once because the consumer checks whether it's already seen that message and skips if it has. That's the distinction to keep in your head. Exactly once delivery over a network? No. Exactly once effect through idempotent processing? Yes.
Worth knowing about Kafka specifically, its exactly once guarantee only covers what happens inside the Kafka cluster. The moment your consumer writes to an external database or calls an external API, you're back to making that side idempotent yourself. So my suggestion is assume at least once delivery. Build idempotent consumers. Every message handler checks if it's seen that event ID before and skips if it has. This single pattern prevents a category of bugs that, when they do occur, tend to be nightmares to debug. Double charges on payments, duplicate emails, inventory counts drifting in ways hard to reproduce, all usually traceable to a consumer that assumed it would only see each message once. If you do one thing after this video, go check your message handlers. If they're not idempotent, make them idempotent. You'll thank yourself the first time a network blip causes a retry storm. One malformed message. The consumer throws, the message goes back to the queue, gets retried, throws again, retried again, and meanwhile, every message behind it waits. In an ordered partition, the entire partition is now frozen. The industry term is a poison message. One of them can take down a pipeline handling millions of good messages a minute. The fix is a dead letter queue. After a configured number of attempts, the bad message gets moved to a separate holding area. The main pipeline resumes. The poison message is preserved for you to look at, not retried into oblivion, not silently dropped. Easy enough. Most teams get this far, tick the DLQ box on the architecture review, and go home. But a DLQ without a replay path is a graveyard. You set up the DLQ, messages land in it, you fix the bug that caused them, and then what? If there's no tooling to push those messages back into the main queue, you have three choices. Write a one-off script under time pressure, replay them by hand, or admit they're lost. Most teams quietly pick option 3. The replay path is the whole point of having a DLQ. Everything else is just setup. The other pieces matter too. Cap your retries, alert on DLQ depth, attach failure metadata so future you can debug. But make sure to build the replay path. Without it, your DLQ is just where problems go to be forgotten. It's 3:47 in the morning. The pager goes off. The broker is out of memory. Not because of a bug, because the producer was writing faster than the consumer could read, and had been for hours. 10,000 messages in, 2,000 messages out. That gap doesn't close itself. Millions of messages piled up. The only question was whether memory, disk, or patience ran out first. There's a quieter version of this bug that's even worse. Nothing crashes. The queue just grows. Messages get processed 2 hours late. For a fraud check on a credit card transaction, an answer that arrives 2 hours late is the same as no answer. Backpressure is the umbrella term for how a slow consumer pushes back on a fast producer. There are a lot of techniques. In practice, you'll reach for 3 of them. 1, bounded queues. Cap the queue size. When it's full, the producer either blocks or fails fast. That's the one to reach for first, because it fails loudly. Errors surface. Alerts fire. You find out while you still have time to do something. 2, auto-scale the consumer side. If queue depth crosses the threshold, add more workers. Works well when your consumers are stateless and your workload is spiky. 3, credit-based flow control. The consumer tells the producer how many messages it's ready for. The producer sends that many and then stops. This is the model behind reactive streams. Project Reactor, RxJava, Akka. Nothing moves unless the downstream side has asked for it. The takeaway from that 3 a.m. page: every queue has a limit. Either you pick it and you plan what happens when you hit it, or the OS picks it for you by killing the process. The second version is always costly. Okay, the question you probably came here for: Kafka, RabbitMQ, or SQS? These 3 aren't different flavors of the same tool. They're 3 different categories. Kafka is a log. RabbitMQ is a broker. SQS is a managed queue.
RabbitMQ's superpower is in the arrows. A message doesn't go to a queue directly, it goes to an exchange, and the exchange decides which queues it belongs in, based on rules you configure.
You can route by exact match, by pattern, by headers, by broadcast, all declared in configuration. No consumer filters anything. The broker does the routing for you. And once a consumer acknowledges a message from its queue, it's gone. Reach for RabbitMQ when the routing is the interesting part of your problem. Background jobs with different worker pools. Workflows where message shape decides destination. Systems where per-message delivery control matters more than raw throughput. In RabbitMQ, a consumed message is gone. In Kafka, messages get written to an append-only log and stay there. 7 days, 30 days, forever, whatever you configure. Consumers track their own position, which means any consumer, at any time, can rewind. Ship a new fraud detection service on Tuesday. On Wednesday, point it at the log, reset the offset to 30 days ago, and let it catch up on a month of history by lunchtime. You don't have to re-emit anything. The log is the history. That's why Kafka shows up in event sourcing, stream processing, and data pipelines between teams. The log becomes a source of truth. New consumers can join any time and see everything that happened. It's also built for throughput, millions of messages per second at the high end. The catch, Kafka has real operational weight. Running a full Kafka cluster for 3,500 messages a day isn't an architecture decision. It's a resume decision. And you pay for it every time someone has to learn it, tune it, or debug it at 4 a.m. Quick update. Kafka 4.0 added share groups, which give you queue-style consumption natively. So the old Kafka can't do queues line is out of date, but the log is still the reason to reach for it. SQS is the whole product in 3 API calls. Nothing to install, nothing to tune, nothing to patch. It runs inside AWS. You send, you receive. That's it. 2 flavors. Standard, at least once with best effort ordering and effectively unlimited throughput. FIFO, strict order with what AWS calls exactly once processing. FIFO throughput starts at 300 a second and can go into the tens of thousands with high throughput mode. Same trap as before, that exactly once is deduplication on the send side inside a 5-minute window. On the consume side, if you don't delete the message before its visibility timeout expires, SQS hands it back to another consumer. The network limits we covered earlier didn't go away. Your consumer still needs to be idempotent. One thing SQS doesn't do on its own is fan-out. For PubSub on AWS, pair it with SNS or reach for Event Bridge or Kinesis depending on the use case. Use SQS when you want a queue, not a commitment. Replay history, Kafka. Rich routing, RabbitMQ. On AWS, want zero ops? SQS. That's the whole decision, 90% of the time. But the teams sometimes pick the biggest tool because it's on the architecture diagram at their favorite company. I've seen systems running full Kafka clusters for 40 messages an hour. 40 an hour. Every on-call rotation on that team became a Kafka tutorial. Every new engineer spent their first week learning a distributed log they didn't need. Every incident took longer because the tool was more complicated than the problem it was solving. Pick the simplest tool that meets your real requirements, not the requirements you imagine you'll have in 3 years. SQS or a managed RabbitMQ will get most systems where they need to go. You can migrate to Kafka the day you have a real reason, and the day you have a real reason, you'll know. One last thing before you close this tab. Open your code base. 3 checks. 1. Grep your consumers for idempotency checks. If they just process every message they see, you have a bug waiting for a retry storm. 2. Find your DLQ and try to replay a message from it. If there's no clear way to do that, you have a graveyard, not a recovery tool. 3. Check whether your queues have a max size configured. If they don't, the OS has configured one for you, and you'll find out what it is the hard way. If this was helpful, please like, subscribe, and share it with a developer who'd find it useful. Thanks for watching, and see you in the next one.